So we are going to take the final version like I wrote it over there, and you are going to transform this into an integral. How about that, all right? This is the proof of integration essentially. And so a lot of students will struggle with this. On the AP test in college, it's just so abstract. They'll look at that and go, I don't even know where to start. So I've tried to organize this for you into 5 easy steps so that you can get it right every time, okay? So you're pros, you can do this. Step 1, what was our first step over there? Find delta x. It's still your first step even when you go backwards to the integral, okay? So find delta x. Delta x is b minus a over n, as we know, but you don't even have to do that this time. You can just look for it in the problem. Delta x is the width of each building. Look up here. Isn't that the width that's been factored out? And that's like first rectangle height, second rectangle height, third rectangle height, last rectangle height, right? So 3 over n is your delta x. Just identify that in the picture. Remember that little hint I gave you just a few minutes ago? The 3 is the b minus a. So you know what? When we get to the final answer, I'm expecting an integral from maybe 0 to 3. That would fit b minus a. See, that's a, that's b, right? A to b. What if it was 1 to 4? That would fit. That would give you a gap of 3. What if it's 2 to 5? Dot, dot, dot. So what that tells you secretly is the gap on your integral, okay? So that's a big clue. Now, what was the second thing we did over there? Didn't we do like a whole column of x's? x1, x2, x3, x4? Do your x's, all right? What is x sub 1? Well, over there we did it graphically by visually looking at the picture, right? We don't have a graph over here. We don't even know what graph this is yet, okay? X sub 1, gee, where is x sub 1 up here? Well, I'll tell you what. This is y sub 1, I know that. This whole term is the y, or the height of the rectangle, base times height. The question is, where's the x in there? Okay, you actually have 2 correct answers. I'll accept either one, all right? You could say x sub 1 is, now wait a minute. We have this, you can barely see this over here, right? Okay, wasn't the x the thing that got plugged in? And you can still kind of see it when you look at your y's because it's the thing that got inserted into parentheses, right? You see this? So look for something on the inside, okay? Could 3 over n maybe be the x that got plugged in? Maybe it's 3 over n, 6 over n, there's a pattern, 9 over n, 12 over n going by 3s, right? 3, okay? All the way down to the last one. That is a valid answer. What if you took the whole denominator? Isn't every denominator in math technically in its own set of parentheses? So you could say 4 plus 3 over n is x sub 1. 4 plus 6 over n is x sub 2. That's more what we did over here. Didn't we take like a number, like 1 was on the graph, and then add the increments to it? So my preference, probably take 4 plus 3 over n to make it look more like what we just did. But you can also get the right answer if you just pick 3 over n. Now I'll tell you this, these are usually multiple choice on the AP test, not free response open-ended questions. If you're on a multiple choice, you have to conform to their choices, don't you? And you know what they normally do? They normally take more rather than less. So they try to take as much as possible. Now don't take the 1, we need something left over to state the equation and to state what y is. So don't take everything. But I would take the whole denominator if I were you, okay? So let's do it this way. X sub 2, what got plugged in? 4 plus 6 over n got inserted into that expression, okay? Dot, dot, dot. Now, one extra little tiny thing. It's not much, but there's one extra thing we didn't do over there that we're going to do here because we're actually trying to establish a pattern, okay? So you want to put a little intermittent step in there that the college professors really like. This is for college too. Let's call it x sub k, or sometimes I've seen like x sub lowercase I, or I've seen like all kinds of notations in college. It depends on the professor. Let's say x sub k is my personal preference, all right? X sub k is equal to what? Okay, the first x sub 1 was 4 plus 3 over n. The second x was 4 plus 6 over n. Do you see the pattern? Every x has a 4, every x has a plus, and a fraction bar, and an n on the bottom. The only thing that's changing is the 3, 6, 9, 12. It's going by threes. It should be because the gap is 3, by the way. Okay? So how do I write that as a pattern? 1 produced a 3. 2 produced 2 3s. That's why it's 6. X sub 3 would give you a 9. The pattern is to take the base number, the subscript number, and multiply it by 3 to get this number. 2 times 3 is 6. 1 times 3 is 3. K times 3 is 3K. So they really like for you in college to establish the pattern and to say the pattern of x's. Because remember, we said it was a pattern. It looks like a pattern over here. You want to establish that pattern and say x sub k is going to be defined as that. And then finally, dot, 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 let's do the very last one. All right? X sub, hold on 1 minute. Don't put anything yet. X sub weight was, what was the very last thing that got plugged in? Looks like 4 plus 3n over n got inserted. So we're going to do 4 plus 3n over n. Okay? And I'm trying to make this kind of thing as easy as possible. All right? Now, what about the subnumber? What is the very last term? Wasn't it always x sub n, y sub n at the end? Okay? Let's make sure that works, though. Here's how you test your pattern. Based on x sub k, if I were to change k into n and plug n into the formula for k, I should get 3n over n. Oh, that's exactly what I got. It's working. Okay? That proves your formula works. That also proves one more thing. Sometimes they feel like being tricky on the AP test. Sometimes these curves don't end at x sub n, y sub n. They end at x sub n minus 1, y sub n minus 1. Sometimes they end up one rectangle short if the last rectangle gets crushed and it's like, you know, there's an x-intercept on the graph. If the graph goes all the way down to the x-axis, you'll lose the last rectangle, and it's actually an n minus 1 case down here, sub n minus 1. That can happen. It's tricky. We'll try to do one of those later, okay? So just to make sure this really is x sub n, plug it in the pattern, it is. All right, now let's go to the y's, okay? The y's are the whole thing, the whole thing, the whole thing. Do you have to write 1 over all that? No, shortcut. Let's just say it this way. That's a y, that's a y, that's a y, they're all heights. Let's just say y sub k equals 1 over, don't even write this formula, just say 1 over x sub k, because aren't all these x's x sub k's? So you can say y sub k equals 1 over whatever x sub k generates from this list. That's a nice, concise way to write it in college. Okay? This is almost more for college than the AP test, but it's also on the AP test. And you can organize it any way you want to. I think this way's the best. Okay? Now, we get down to here. The limits of integration. I bet a lot of you, just go back just for a second. Look at this. Maybe like block out the k's, drop the k's in your mind. Can you already tell what function we're integrating? Like you can basically see it right here. So I think we already know what function we're integrating. But what about the limits of integration from 1 to 3? Or from, in this case, 0 to 3, 1 to 4, 2 to 5? I don't know which one it is. We need to find which one it is. Some of you can spot it. Some of you are very clever. Some of you may not be able to spot it yet. Okay? Let's find what we call the limits of integration, the boundaries of integration. All right. How do we do that? Okay. Our limits of integration are those x's or y's. How do they get plugged in after you integrate? Don't we plug these numbers in for x? These are x's. We call them a to b, but we also call them x sub 1 to x sub 2, for instance. Okay? In this case, the limits of integration come from the first x and the last x. Your limits of integration are x's, so you should be looking first last, which you can kind of see it up there too. All right, this is the other thing we didn't do over there that you have to do here, because you don't know which one of these boundaries it is. Okay, let's take the first circle. 4 plus 3 over n. All right, that's some location of a rectangle, but that's not giving me the actual x-coordinate. Some of you can see it in there. Here's what you do. Take the limit as n approaches infinity. Because isn't the number of rectangles blowing up to infinity to fill up the entire shape perfectly? Apply that limit to the first x-coordinate. Okay? Let me show you this on the graph over here. How did we know that the left boundary was 1 and the right boundary was 3 on this last problem? It was given. I gave it to you, right? But now, right now, we don't know what's happening. Okay, so let's take those out right there. So imagine this. We've got question mark, question mark. We have no idea where we are right now in this new equation, okay? If you could take the limit as n approaches infinity, wouldn't that blow up infinite number of rectangles, but at the same time, isn't it shrinking all the widths so that the buildings get infinitely skinny or infinitesimally small, right? So here's what happens. If you take the very first marker, which is, what is it currently? It's 4 plus 3 over n in our current problem, right? That was our first x. Isn't your first x like where the rectangle comes up, right? So if you take the limit as n approaches infinity, it's going to shrink the rectangle width lower and lower and lower and lower, and it's going to draw this towards this question mark right here. See, it's pulling them together, kind of like the limits we've done in chapter 8. And if it pulls this in, it's going to tell you what it's gravitating towards. It's going to tell you exactly what number that is right there, that question mark. Okay? Interesting. So watch this. The limit as n approaches infinity. What did we say in chapter 8 about infinite limits? Gem number 1. Take infinity and just try to plug it in. Oh, yes, you can. 4 plus 3 over infinity. That is 4 plus 0. That is 4. How about that? Some of you already knew that. 4 is the left boundary. See, it's dragging this and it's pulling it over to apparently 4. Oh, that must mean 4 is sitting right here. You also could have seen it with the 4 plus there. But now, wait a minute. What about those people who only chose 3 over n and you didn't choose 4? Well, see, that could alter the answer. So I trust the limit, though. The limit will tell you where to go. Okay? Now, at the other end, all right, the b, that's the a is 4, the b. Take the limit as n approaches infinity of the last x, and it will bring it to the other side of this graph and figure out what the right boundary is. 4 plus 3n over n. Okay? All right, so if you plug in infinity, you get infinity over infinity. So that doesn't help. That's indeterminate. All right? So we've got to go to something else that's actually very obvious. Just cancel out the n's, and you get 4 plus 3 is 7. Now plug in infinity. There's no n left. So 7, when you plug in infinity, is just 7. Aha! We're integrating from 4 to 7. Those are your limits of integration. And I do mean limits of integration. Can you believe all this time this year when we used to call these limits of integration because limits mean boundaries of integration? Can you believe the real origin of that phrase is that limits of integration are literally limits of integration? They're limits. I love that. I love how that happens in this class. And then, wait, even something greater happens later, okay? You'll see. Okay, so step 5, what's your answer? We are integrating the function. Let's take out the k's back up here. Don't take it out of your notes. I just want to show you. Oh, the function was y equals 1 over x. We're integrating 1 over x. Okay. It's the integration of 1 over x. You have to put a dx from 4 to 7 according to the limits. And I do say limits of integration. From 4 to 7. Oh, that fits the gap of 3 like we predicted. That whole gigantic, kind of scary looking phrase up there with an infinite limit in front, trying to shrink all your rectangles and buildings down, just meant this. So that's how Riemann defined this. It actually wasn't until years later that the mathematician Darboux, who we talked about in the first semester, figured out that, oh, we can actually just do integration instead of having to do all this like Riemann's doing, all right? Still huge breakthrough, okay? It does not say find the answer, it just says write the integral. If you did have to find the answer, well, the integration of 1 over x is clearly natural log of absolute value of x, right? So then what would you do? Well, you just plug in top minus bottom and you get natural log 7 minus natural log 4, you know. So you might have to do that sometimes. Sometimes you just write the integral, okay? Interesting, though, that number 119 ranked Napier, who I don't think we've ever talked about, Napier didn't know integration because it was 1614. He didn't know Riemann sums because Riemann didn't even live until the 1800s, right? But Napier in 1614 tried to get the area under 1 over x. And he kind of used like little increments and little approximations, roughly like the rectangles. And that's how he discovered the existence of natural log. Napier was the first human to discover natural logs by trying to get the area, which would turn into integration later, under 1 over x. And he called it logarithmus naturalis. There's some kind of natural log that occurs in nature, and it is the area under this curve. First person really to really try to get the area under a more complex curve than Archimedes, who worked under the parabola in the BC era. Amazing how all this history comes together. So now over here, we've got letter C. Mr. Wade, what have you gone and done? I just got that over there, and now you got this weird looking thing called a sigma, the capital S in the Greek alphabet, all right? The capital S, it stands for the word synapse, all right? And this symbol was first used by number 1 ranked Leonhard Euler. He said from now on, synapse, which was of course Greek for synopsis or summary, like a summary of a movie, okay? This is going to mean summary from now on. We dabbled in this in integrated 3. I hope you did it in pre-calculus. The sigma means to sum up a bunch of things in a pattern. I think we did it with like a bouncing basketball or something like that back in integrated 3. So here's the thing. All this means is take 1 for k, plug it in. Take 2 for k, plug it in. Integers only. Take 3 for k, plug it in. 4, 5, 6, 7, 8, and then stop when you get to the top number. Okay? So a little quick refresher if you forgot this from integrated 3, or if you were never taught this in pre-calculus, quick refresher. You are allowed to write this out the long way if you want. Of course, I'm going to show you how to do the shortcut. This is the limit as n approaches infinity of, if you plug in 1 for k, you will get 3 plus 4 over n times 1 quantity cubed times 4 over n. Sigma means summary. Plus, the second term would be plugging in k equals 2. 2 times 4 is 8. 3 plus 8 over n quantity cubed times 4 over n plus ... until you get to n and you stop at n. Oh, wait a minute. It's the same thing. It's the same thing that we just did. It's just written a lot more concisely and together. And Euler is one of the people who proposed we need to write this more concisely and not so long. Okay? So this does mean the same thing over there. All right? You're still going to do your 5 steps. Step 1, tell me what delta x is. Do you see the 4 over n, the 4 over n, the width of every rectangle is the same? Can you spot it here? Does it kind of stand out as a b minus a over n? All right? First thing I want you to do. Hey, if the gap is 4 from a to b, that's b minus a, I'm thinking 0 to 4, maybe 1 to 5, could be 2 to 6. Maybe it'll be 10 to 14, but we can narrow it down now. We know the gap. We'll have to find those later. All right? Step number 2. List your x's. This is the only long step, really. All right? What are your x's? What appears to have been plugged in? You can see it here. You can see it here as well. All right? Would you say that maybe the 4 over n k is being plugged in, you could do that. Not my preference. I prefer to take as much as possible. Remember, take as much as you can. Would you say that the 3 plus 4 over nk might be the whole thing being plugged in? I like that better. Don't take the cube. You got to leave something for the original function, all right? So it looks like, now, kind of a shortcut here. I've already put the k's in for you. Instead of you doing the whole list, I put the k's in for you. You can jump straight to that step over there. X sub k, the thing being plugged in or inserted, must be 3 plus 4 over nk. Doesn't that look just like the x sub k over there that we just did? Right? It's like some whole number plus some little increment of little widths of buildings, right? Okay? That's all you have to do right there. The y's. So you always do delta x, x's, y's. The y's, okay? Wasn't this delta x, so isn't this like the base right here? Isn't this whole thing with the cubed the height? Do you realize that this is just base times height from middle school? But it's summed because there are going to be infinite rectangles and you're summing them all up together. See, n is approaching infinity. So the number of rectangles is approaching infinity there. So, all right, this is just base times height. Delta x is the base of each rectangle. This whole blob right here is the height. Let's write it very nicely and concisely. Y sub k is apparently x sub k to the third power. Okay? X was the thing being inserted. Y is kind of the operation that's happening to it. Oh, it's being cubed. All right? Now you're looking really good. For step 4, we're going to do our limits of integration. I say limits of integration. They're actually limits. Can you believe it? So limit as n approaches infinity, since that's what's happening. We're shrinking the rectangles so skinny that they actually make the perfect area under the curve. Limit as n approaches infinity, applied to the first x. If you write it out, you can see the first x. Inserted 3 plus 4 over n. If you didn't write it out, which takes time, and I probably wouldn't do that in the future, couldn't we just plug in the number 1, which was our start point, into the formula? It says k is 1. X sub 1 is 3 plus 4 over n times 1. So you can get it from here too. I'd rather you get it from here. Okay? All right. So take infinity, do an infinite limit like chapter 8. That'll give you 3 plus 4 over infinity. 4 over infinity is 0, and 3 plus 0 is 3. Aha! One of my limits of integration must be 3. We're integrating from 3 to something. We're on to it now. They can't fool us anymore. Let's do the final limit of integration. The upper limit of integration. Okay? All right. It starts at k equals 1. Where does it stop? At n, which is really going to infinity, but we got that covered with the limits. It's going to stop at n, or whatever they put on the top. Okay? Take n, put that in for k. X sub n, last stop, is 3 plus 4 over n times n. Okay, times the n. If you plug in infinity this time, you get infinity over infinity, indeterminate, but you can cancel your n's. 3 plus 4 is 7, again, just like over there. Aha, we're integrating from 3 to 7. Is that a gap of 4? It is a gap of 4, yes. Final answer. What was I integrating this whole time? What is this, the fancy way of Riemann writing? It's the integral from 3 to 7, the limits of integration. Hide your k's. It's y equals x cubed. That's the function. You must be integrating x cubed dx. Okay? Does it say just write the function, or does it say actually find it out? It says just write the function. Just express it as an integral. Don't actually find the answer. All right? I don't want to do x to the 4th over 4 and plug in 7 to that anyway. Okay, hopefully it's making sense now. You can see it with the sigma. You can see it written out. Okay? All right, last one. Now let's see if you can recreate what we did in the very beginning of class today. I gave you an integral of e to the negative x earlier, and you turned it into, together, we turned it into this long expression. All right? So, let's give it a shot, okay? Let's retrace the steps. But it took a long time in the intro. Why? Because I was trying to carefully explain it where your brain could absorb it. Now I want to see if you can do it at lightning speed and just do it, all right? Just complete the problem. Okay, we always start with delta x, then x's, then y's. Every time, doesn't matter which way we're going. Okay, doesn't matter if it's sigma, the long expression, and the integral. So, delta x, b minus a over n. Let's just put an equals there. B minus a over n is 5 minus 2, so there's a gap of 3, over, we're going to keep that n. The number of rectangles is going to be n. Of course, we're going to let n approach infinity, right? But the number of rectangles must be n, okay? So that's going to be 3 over n. Easy to get. All right, now, without even drawing a picture, doesn't this graph start at 2? We're blocking it from 2 to 5, which is why we say from 2 to 5, never 5 to 2, right? Integrating from 2 to 5. The starting x sub 1, would be starting at 2 plus the width of the first building, because we're trying to get to the right-hand side of the first building, okay? And I just always do a right-hand sum instead of a left-hand sum. It's easy just to always do that, okay? And they usually do that on the AP test. Isn't 3 over n the width of each building? So 2 plus 3 over n is your first step, okay? X sub 2, still starting at 2 plus the width of 2 buildings. 3n and another 3n makes us 6 over n. Dot, 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 and then that's going to go forever. And then we establish our pattern, which is x sub k. Now in the sigma problem, I just gave you x sub k. It was sitting right there. In these, when you're trying to go from the integral to the longer form, you probably want to establish your own x sub k because, again, in college they love that, okay? So, the pattern is, everybody has a 2 plus, something over n. It's just the something that keeps changing. First term 3, second term 6. Oh, it's just subscript times 3 again. Subscript k times 3 is called 3k. That formula will generate all these and all the infinite possibilities right there. Okay? All right. And then normally we do like the dot, 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 and we do the last, the x sub n at the very end, although we don't really know if it's an x sub n or x sub n minus 1, so you don't have to do that in this version when you're going from integral to expression. But if you go from expression to integral like letter B, you'd probably want to go ahead and put in that last term right there. But really, you don't need much to do these. You really don't. I'm showing you more information than you need to help you for college because you need all this. But really, on the AP test, it's so simple that you just know your b minus a over n. You just kind of see the pattern of the x's, and then you say, oh, every y sub k, at every point, the height of the building would take the x and plug it into the original function x squared. So instead of x squared, let's call it, actually let's go ahead and plug it in. Let's call it 2 plus 3k over n quantity squared. So see what I did there? All right, I'm trying to make it look like the sigma one we just did over here is what I'm really thinking in my head. Okay, so all these wires all over the place. So y is any x at any place, that's every possible x, plugged into the original function. Okay? That's really all you have to do. It's just that easy. All right? Now, what's our next step? We have to try to figure out what is the base and the height of each one of these rectangles. All right? Good way to say this. Didn't we just say that the sigma notation is just a summary of a bunch of base times height, base times height, base times height? Watch this. The base of each rectangle is always delta x, 3 over n. Always, okay? A little delta x. Matter of fact, I may have put that on the notes already for you. I did not. Put it over there, all right? The height of each building or rectangle is that expression right there. See how I'm recreating the sigma, but we're going backwards now? Okay? There's your base, there's your height. The area of a rectangle is base times height. So we're going to multiply those two together. Although usually they put the base at the end. If you kind of noticed before, it was at the end. So it doesn't matter to me. But I know on the AP test, they always put the base at the end. Okay? Base times height is the area of each rectangle. Now that only covers one rectangle. Don't we want to cover all the rectangles? So we're going to bring in a sigma, because in this problem it says write this in sigma notation. All right? So, sigma notation. We are going to sum all the rectangles from k equals, the first one was x sub 1, up to the last one, which is x sub n. That will give you still a finite number of rectangles, though. How do we crush the rectangles infinitely skinny and make them into a full area under the curve? Take the limit as n approaches infinity. And you can actually write the sigma notation of an integral. And if I had showed you that on the first day of school, you would have freaked out and said, there's no way I'll ever understand that problem. And now, you got a shot. Hopefully after just one lesson, a lot of you understand it. If not, practice the problems. You'll get better at this and it'll make sense, okay? This is probably a good time to show you this, because I'm just going to blow your minds right now. Sigma, according to Euler, stood for synapse. Now, Euler's good friend Jacob Bernoulli invented the integral symbol, didn't he? He was the first one to come up with that. We mentioned that before. The integral is Latin. It's a capital S, that is an S that's been stretched. It's Latin for summa, or summation, because what is integration? A summation. What is sigma, which is Greek? Synapse, which is also summation. All right? So you see, that's an S, and the integral is an S. They're both an S. So watch this. The integral is just like the sigma. So that really is an integral, all right? Now, this right here, isn't 2 plus 3k over n the x? Isn't that really x squared? Oh yeah, that's what we were doing up there. Okay? Now, isn't 3 over n called delta x? But guess what we call delta x these days in modern high school and college classes? Delta is the Greek letter for d. Oh my goodness. That's why we write integral and dx, because that's actually delta x. That's just width, height, because the equation is always height. And the integral is the same thing as sigma. That's one of my favorite jaw droppers of the whole year right there. You mean the whole first semester when we did delta x and then sometimes we did dx, they were the same thing? Same thing. All just different origins. But Euler and Bernoulli were working together. They were partners in math. So big surprise, they kind of ended up with different ways to write the same thing. Amazing. I love this. I love this stuff right here. All right? Fascinating. Okay, so that'll do it for that section. Go on to, you can do the homework. You can also do the next video and enjoy.
Hold it now.
Is 1 plus 1/5 plus 1/5. That's 1 plus 2/5. Number 12 ranked Riemann was the person, if he hadn't discovered it, they'd then be so, and then really cool to see this right here. I'm in the way.